happens in 2 dimensions. So if I wanted to graph this, it will be a circle centered at 0, 0 with a radius of 3. So like this, minus 3, 3. Very simple. But what happens if we are in 3 dimensions? In 3 dimensions, what you do is basically first you have the circle here. You can see the circle is drawn here in the plane x, y. But because there is no z in the equation, then this circle, you slide it up like this, and you slide it down, which means z can be 1, 2, 3, 4, 5, or it could be minus 1, minus 2. At each value of z, you have a circle, and you put all these circles together, what will you get? You will get this shape, which is called a cylinder. So this is a cylinder in space, okay? So same thing, if I have, for example, x squared plus z squared equal to, let's say, 16, what will be the graph of this? Again, a cylinder. Well, it's a circle, but in 3 dimensions, it will become a cylinder. What is the axis of the cylinder this time? The y. So it will be like this, yeah? It will be a cylinder going in this direction, in the y direction, like this. And this cylinder, its radius is 4, yeah. So it's going to go through 4 here and minus 4 down. So its radius is actually equal to 4. So you will get this cylinder with the y-axis as the axis of its cylinder. Are we okay with this? Yeah. So x squared plus y squared equal to 9. In 2 dimensions, it's a circle. In 3 dimensions, it's a cylinder. It's like this. Yeah. That's basically what this is. Now, in the same way, if you have this equation, z equal y squared, in the plane yz, what is this shape? It's a parabola, yeah? It's a parabola. So if you graph it just in the plane yz, it's a parabola. It's actually here. You can see it. I think that, yeah, it's this one here. It's this. So this curve is the parabola z equal y squared in the plane yz, like this. Now, because there is no x in this equation, so what do we do with this parabola? We slide it along the x-axis. So this parabola goes in this direction, and it goes in this direction. So it will give you the shape, which is called a paraboloid in basically in 3 dimensions. Yeah. So you get this shape, or this one here. So that's the general idea of these equations. So you graph in the plane yz, and you just slide it along the x-axis, so you will get this. In the same way, if I say, yeah, if I want to graph y equal x squared, so in the plane xy, it's going to be, what shape is it? It's a parabola, yeah? It's a parabola in the plane x, y, like this. Y equal x squared is this parabola. Then what happens to this parabola? We'll slide it along the z-axis, yeah? So it's going to give you something which looks a bit like this. Can you see this? So it's going to be a surface, yeah, in like that, around. It's at every value of z, you will get a parabola y equal x squared. So that's the general idea of these graphs. Okay. All right. Now, here, another type of equation. This, I think we have already seen this equation before. Do you remember it? What shape is this? It's a sphere, yeah? This sphere, what is its center? A, B, C. That's the center of this sphere, yeah? So this equation describes a sphere in space where the center is A, B, C, and the radius is R. Yeah, it's basically R squared, so it's like that. If you want to write the sphere centered at 0, 0, 0, what will be the equation here? X squared plus y squared. Basically, A, B, C are 0. A, B, and C are all 0. So you will get the equation x squared plus y squared plus z squared equal to r squared. So this is the sphere centered at 0, 0, 0. So center ABC here, center 0, 0 is here. Now, a general equation, it's like a sphere, but here we have numbers D, E, and F in the denominator. In this case, it's not going to be a sphere. It's going to be, it's like a rugby ball, yeah, like this. Can you see this? This shape here, an ellipsoid. That is basically the, if you have an equation of this type, the shape will be like this. Now, if you want to graph, for example, this, yeah, suppose I want to graph this, you know, the equation is here. I want to have an idea about the graph. So what you could do is, you could look at the way this surface will intersect the axis. For example, on the x-axis. What happens on the x-axis? Both y and z are 0, yeah? So you will get the equation x squared over 1 equal to 1. So what are the values of x? Plus or minus 1, yeah? And basically, you can see here, this will be 1, and on the other side, it will be minus 1, yeah? And we go back and see what will be the intersection with the y-axis. What happens on the y-axis? X and z are both 0, yeah? So you put x equal to z equal to 0. So this, yes, Salha, it's always 1 here. This is 1, yes. If it's not 1, then you need to, if it's 4, for example, you need to divide everything by 4 to make it 1. So you can always change the equation to make it equal to 1, yes. Okay, now on the y-axis, let's see how this curve or surface intersects with the y-axis. X and z are 0, So you will get y squared over 4 is 1. So the two values of y will be plus or minus 2. So you can then see that in the graph, the y-intercept, this is 2, and the other side it will be minus 2. This is the y-axis. Finally, what are the intersection with the z-axis? Yeah, so on the z-axis, the values of x and y are both 0. So then you get z squared over 9 is equal to 1, which means z will be either plus 3 or minus 3. And you have the intersection at minus 3 and 3. And then you can graph the shape which goes through all these. How many points did we find actually here? 6 points. So we found actually 6 points, and you can use these 6 points to give you an idea about what the shape will be. So any equation of this type, yeah, will be an ellipsoid. Yeah. And the center, what are the values of ABC in this example? 0. So this ellipsoid, its center is 0, 0, 0. Of course, you could have it somewhere else. It may be centered at another point. But in this example, its center is actually the point. It's right here. It's 0, 0, 0. Okay. By the way, we will need these ideas about graphing later when we do integration, double integration, triple integration. You need to know how to graph these. Not very difficult. So you need to just memorize 4 or 5 types of graphs, and you would be okay. So here we have x squared plus y squared is equal to z. I want to graph this. What is it in 3 dimensions? So we can just think a little bit about what happens. For example, if I take the value of z equal to 1, yeah? So here is, so let me, what happens when z is 1, for example, in this equation? I will get x squared plus y squared equal to 1. What is this equation? Okay, but because z is 1, so it's not the whole cylinder. It's not half a cylinder. If you take a cylinder, but only at z equal 1, it becomes, take the whole cylinder, but I want to slice it with z equal to 1. What will you get? A circle. It's going to be a circle. Can you imagine that? You have a cylinder like this, but I want to look at it only when z is equal to 1. So only at one particular height. So at z equal 1, I will get a circle of radius what? Of radius 1. So at z equal 4, for example, I get a circle of radius 2. So when z becomes 4, my circle now becomes a circle of radius 2, like this. And in the end, if you put all these circles on top of each other, what you will get is a shape which looks a bit like this. And yeah, and I think it's graphed down here. You can see the shape is here. Are you okay? Or, yeah? So you will get, this is called a paraboloid, basically. it's not, these are parabolas. I will tell you why it's a parabola here. Yes. Well, exactly, yes, absolutely. You're absolutely correct, yes. If it is a number here, constant, 5, 6, 7, 8, then it will be a cylinder. Why do you think it's a cylinder? Because these circles will all be the same then. Do you see what I mean? If you put 4 here, then every circle will have a radius of 2. So they become a cylinder. But because it's Z, then Z is changing. When Z is 1, it's a small circle only of radius 1. When Z is 4, it's a circle of radius 2. When Z is 9, for example, when you take Z equal 9, what will be the circle? Radius 3. So it's opening up and up like this. So in the end, you're getting a shape which is like this. Good question. Okay. Also, you can see that, yeah. For example, on the YZ plane, if I want to know what is the intersection with this surface, and the YZ plane, that means what? On the YZ plane, what happens? The x is 0. Very good. X is equal to 0. Then, if I substitute, I get z equal y squared. What is the graph? What shape is z equal y squared? It's a parabola, yes. It's a parabola. That's why this is not a cone. I will come back to cones in a moment. This is a parabola. A cone must have a straight line. Yeah, and we will talk about this in a moment. So it's not a cone, it's a parabola. Yeah. So it's a paraboloid in the end. This is what we get in these equations. Of course, if you could have, in a similar way, you could have x squared plus z squared equal to y. Then it will be exactly the same shape, but what is the axis then? What is the middle of the y-axis? Yeah, it's like this shape, but along the y-axis. Right. Yeah. Now, one last point before I move away. Why there is nothing below the xy plane? Why there is no graph below that? Sorry? Z is? What happens, by the way, below the xy plane? What are the values of Z? Negative, yes. And you can set this equation. Can this Z be negative? No, because it's x squared, which is positive, plus y squared, which is also positive. So this is telling us Z will never be negative. It may be 0, yeah, when x and y are both 0, so it's okay. We have a point here, but nothing happens below the xy plane, which is where Z is negative. So basically, we're only getting this part of the graph. Okay, now here, slightly different thing. In what way is this different from what we just did? How is this equation different from the previous one? That is? cannot. So, if you look carefully at the equation, before we had z, yes? Here we are having z squared. That's the main difference. And this will make a big difference in the shape, by the way. Because what will happen now? Yeah. Okay, we will have negative values, first of all. Z can be negative here. So we'll have, in the graph, we'll have some parts up and some parts down, first of all. What will also be different is this part here. So let me, yeah. It's not going to be, this is a parabola. This, remember, was a parabola, yeah? Here, we will not get a parabola. We'll get something else. So let's check this. So first of all, I could take different values of z, like z equal 1, yeah, x squared plus, oh, okay, there's also a difference. Here we're having y squared over 4, yeah. And then I will get 1 here. Now this shape is not exactly a circle. What is this shape? It's an ellipse. Yes, it's an ellipse. Yeah. So basically, this time, each z will give us an ellipse, not a circle like we had before. So when z is 1, I will get an ellipse like this. Elliptical shape. Here, I will get another ellipse with a bigger y will be, yeah, when z is 4, then the y will be bigger, and so on. So I will get also down, same thing, because when z is minus 1, for example, again, because of the square, you will get x squared over 1 plus y squared over 4 equal to also 1, yeah? Yeah. So if we go down, it will also be an ellipse down here. That's it. Now, what happens on, let's say, the YZ plane? Let me check what will be. If I want to, the way the curve cuts the YZ plane, what happens on the YZ plane? X is 0, yeah? So x, yeah, thank you, Aisha, there. Okay, so x is going to be 0. So you will have y squared over 4 equal to z squared, which means z will be, by taking the square roots of both sides, it will be y over 2, or perhaps minus, yeah? What are these lines? What are these? What are these equations? Z equal y over 2. A bit like if, yeah, a bit like if I say, what is the equation of this? What is the graph of this equation? It's a line, yeah. It's a straight line with a slope of half, yeah. It's a straight line. Y will be, so the graph will be like this, yeah. Y equal, and y equal minus half is also a line, but this time like this, yeah, the other side. So if we come back here, then what we're getting is a line here, and we're getting also a line here, and you have your circles, your ellipses like this, and in the end, what shape is this? What do we call this shape? It's a cone. Yes, it's basically a cone, an elliptic cone. Can you see that? Yeah, roughly. Yes. So each value of z is giving us an ellipse, which I drew here in green. and the intersections are straight lines, so that's a cone. Finish. Yes.
But you choose the number of Z.
Sorry?
You put any number of Z, for example, 1 or 1.
Yeah, you can choose any. You can put any Z you like. If you put Z equal 9, you can get an ellipse also, big ellipse. Yeah, Z equal 9. That means you're up here. The equation, when you graph this equation, when you graph it, it's an ellipse which goes through y equal plus or minus 2, like this point, yep, and x, if you want to look at where it, x will be plus 1 minus 1, so you have this ellipse, which is there. Yeah. So these values of z are just chosen to show you a little bit how things work. Okay. Okay, I think that's basically what there was here. All right, let's have a look at some examples, and then we can move on. Z equal x squared. What is this? It's a parabola. Of course, if you graph it in the plane xz, it's a parabola. But in space, what do you do then with this parabola? You slide it along the y-axis, exactly. So its shape, so let's see if we can graph that. Not always easy to see how things work. So first, you graph in the plane x, z. It's going to be a parabola like this. And then this parabola, imagine sliding it along the y-axis. So what you will then get is something, so let me, maybe like this. Can you see this or roughly? Yeah. So parabola all the time going like this. And it's open from the top, yeah? You can see that at every y, it's a parabola. Like this one, we did an example like that just a moment ago. So what is this shape? It's an ellipsoid, like that. If you want to graph it a little bit more precisely, what did we do to graph this? Yeah, so you need to check the intersection with the x, y, and z axis. So where will this surface cut the x-axis? At the point on the x-axis. 1, yeah? 1 and -1. So it will cut the x-axis at 1 and -1. It will cut the y-axis where 3 and -3, yes. Good. So 3 here. 1, 2, 3. And on the other side, -3. And it will cut the z-axis. at 2 and negative 2. So it will cut this at this point and also at this point. So now, I don't know how good at you are at drawing, but it's a bit like this. Yeah, like that, and then you will have something like this. I will show you. Does it look okay? Yeah. So something like this, and then are we okay with this? Yeah. That's something like this. This one. So here, at every value of z, if you take z, for example, equal 4, what will be the shape you will get? For x squared, yeah. If you take z equal 4, for example, you will see that the equation becomes 4x squared plus 4y squared is equal to 4, which means x squared plus y squared is equal to 1, which is what? It's a circle. So at every z, you will get a circle. Circles. And of course, this radius will increase. But is it a cone or is it a paraboloid like this? It's a paraboloid because you can see that this is a parabola. Z equal 4x squared is a parabola. So therefore, yes, you can, I think you can see now the shape will be something like this. X, Y, Z. Does that make sense? Yeah? And at Z equal 4, like we said, if you put 4 here, then you will see that you will get a circle of radius 1. At this level, at Z equal 16, you get another circle. At 16, what will be the radius at 16, by the way, when Z is 16? 4? Not 4. No. If Z is equal to 16, put 16 here, put 16, and then divide everything by 4. You get x squared plus y squared is equal to 4, which means the radius is 2. Yes. So at z equal 4, the radius has increased. Sorry, at z equal 16, the radius has increased to 2. It's still quite, quite narrow. So it's not increasing very quickly. So at 4, the radius is 1. At 16, the radius becomes 2, etc. So the radius increases, but not in any way, great way. Here, at every z, if you fix a z, like 10, whatever, you will get what shape is this equation? It's an ellipse, yes, it's an ellipse. Okay, so it's an ellipse, but now is it a cone? Is it an elliptical cone, or is it a paraboloid? It's a cone because why? Because it's a square, exactly. Because if you look at this equation, you get the straight line. Yeah, z squared equal to 4x squared. That means z is actually 2x, or z equal minus 2x. These are lines, and therefore the graph is actually going to be a cone. Yes. So again, that means you will have part of it where z is positive, but you will also have part of it where z is negative. It can be positive or negative. So in the end, you will have a cone like this, so with different, yeah. So it's an elliptical cone. Are we okay with this? Right, that's it. That's all I wanted to say regarding these surfaces for the moment. Later, when we study integration, I will do some reviewing. I will show you a little bit. Anything you will need, I will review it with you. So that is this section on. Any questions before I close this? Okay. Let's just
Doctor, we finished chapter 10?
sorry.
We finished chapter 10? We finished chapter 10?
Yes, we did. Yes, we did. This is the last section of chapter 10. Yes. And actually, I will not, 11, we will leave it until later. That's the way the syllabus is organized. So we will move on to chapter 12 now. The first section is talking a little bit about functions of several variables. Hopefully a bit more, a bit easier perhaps. Okay. Okay, so 12.1, functions of several variables. Up to now, of course, I think most of your calculus, most of your math work has been working with functions of one variable. Here, we'll take a look at the functions of two variables, or possibly even three variables, okay? So, here is, for example, an example here of a function of how many variables? Two variables. What are they? X and Y. So it's a function of two variables. It takes x, y, and it will give you a real number r. So it's a function whose domain is in R2. So two variables, and its value is a real number r in the set of real numbers r. So f and g are both functions of two variables. Yeah? These two functions are variable. But you can also have a function of three variables, four variables, etc. Three variables, here is a function of three variables. Here the variables are x, y, and z. Yeah? X, y, and z are the variables here. So G also is a function of three variables. Okay. Like functions of one variable, one of the questions we often ask is, what is the domain of the function here? Find the domain and maybe sketch it. Now, let me remind you something. Let me just take a couple of minutes to remind you the idea of a domain of a function. For example, if I give you this function, and I say, what is the domain of this function? What do you do? So I want to find the domain. The domain means what values of, for which value of x, for which values of x does this function exist, etc. Of course, the square root of something exists only if what you have inside is not equal, greater than or equal to 0. If it is negative, can I find the square root of a negative number? No. So that means the domain of this function, I will find it by solving 2x plus 3 greater than or equal to 0, which of course will give us x greater than or equal to minus 3 over 2. So I could say that the domain of this function are all the numbers from minus 3 over 2 to infinity. That is the domain of this one. So when you have a square root, what is inside the square root must be greater than or equal to 0. That's an example. Another example is, suppose I give you the following function, ln of 3x minus 1. What is the domain of this function? I want the domain, D. You know the function ln, yes? Logarithmic, natural logarithmic function. Now, when does this exist? Yes, basically, take your calculator and try to find ln of minus 1, for example. Try and see what happens. Can you find ln of minus 1? No. So again, for this function to exist, 3x minus 1 must be greater than 0. This time, not equal to 0, because ln of 0, if you try it again, you try ln of 0, what will it give you? Nothing. Yeah? Come back next time. No answer. Okay? So, therefore, you want the domain here, you need to solve 3x minus 1 greater than 0. Again, we can solve this. So, x greater than 1 over 3, and that will give you a domain which is all the numbers from 1 over 3 to infinity. Finally, another important thing to remember when you work with domains is that if you have something like 3x minus 1 divided by 5x plus 4, and you want the domain of this function, yeah. What is the domain of this function? Yes, all real numbers except those which make the denominator equal to, I should not have 5x plus 4 equal to 0, because you take a number, you divide it by 0, can you do that? No, it will not exist. So take 5 over 0, you check your calculator, again, not possible. So everything is okay except when the denominator is equal to 0, so you will get x equal minus 4 over 5. But please be careful, the domain is not x equal minus 5 over 4. What is the domain? Everything except minus 4 over 5. So you could write this are the whole real numbers except minus 4 over 5, or you could write it as minus infinity to minus 4 over 5 union minus 4 over 5 up to infinity. So these three examples show you a little bit how the idea of domain of a function works with one variable. Well, with two variables, it's kind of similar. So let's go back a little bit here. So I want to find the domain of this function here. F x y x ln y. Now, because we have ln y, does it mean about the value of y? Y must be positive. Y must be positive. Yeah? So here, y must be greater than 0. Otherwise, this function will not exist. So now, how do I sketch? Remember the domain now. The domain is in the plane, yeah, xy. Where is the region? So the domain is all xy's in the set in the plane such that y is greater than 0. I can write the domain like this. All xy belonging to the plane R2 such that y is greater than 0. What are these points? For example, if I take a point here, is it in the domain? No. Why not? Because y is negative. So really the domain is all of these points. It's fine. So this is the region which represents the domain of this function a. Take a point here, it's fine. You can find f of xy. So if you take a point here, f of xy is okay. If you take a point down here, xy here, f of xy here, can you find it? No, because y is negative at that point. So the domain is that one. How about b then? What happens in b? This function g, what is its domain? So in this case, what should we have? Y minus x squared should not be equal to 0. Yeah? So this is what you would say. So y minus x squared, I should not have it equal to 0. So that means y, yeah, should not be equal to x squared. That means the domain is everything is in the plane except the parabola y equal x squared. So basically you could sketch that as, yeah, put y equal x squared, and then the domain will be everything except this red parabola here. Okay, so that is the domain of this function g. Do you understand it? Yeah. So can you give me a point on the parabola? Can you just give me a point, 1 point, which is on the parabola? 2 and 2, 2? Yeah, 2, 4. Yeah? X equal 2. If x is 2, y will be 4. Now, can you find g of 2, 4? No, you will not be able to find it. Try. G of 2, 4 will be 2 times 2 divided by 4 minus 2 squared. What is 4 minus 2 squared? 0. So you cannot find it. So if you try any point on the parabola, you will not find g. But any other point is okay. Take any point outside of this parabola, it's okay. You can find the g. So, yes. What I put in green here is the domain of the function. Yes? The red parabola is not in the domain. That's what you look at the whole plane and remove that parabola. Anything which is left is, if you remove the parabola Anything which is left there is the domain of the function g. Yes. So that's basically what we're saying. Yeah. So you could say the domain is basically all xy in the plane such that y is different from x squared, like this. Y should not be equal to x. Okay. Now here, A. Now we are moving to 3 dimensions. There is a function f which has a cosine of x plus z. Cosine, by the way, is defined everywhere, so we're okay. There's no problem with the cosine. But the denominator of this function should not be equal to 0. Yeah? So if you want to find the domain of A, you should say xy should not be equal to 0. Now, what does that mean if we say xy equal to 0? There are 2 ways to have xy equal to 0. That means either x is 0 or y is 0, yeah? There are 2 ways, exactly, yes. Or y equal to 0. Now, x equal to 0 in 3 dimensions, in space. What region, in which region you have x equal to 0? It's the YZ plane, yes, the YZ plane. And in which region is y0? XZ plane. So, what does that mean? That the domain of this function is the whole space except the YZ plane and the XZ plane. So take any point in space, you can find f of x, y, z, except when the point is on the YZ plane. Why? Because on the YZ plane, x is 0. So the denominator will be 0. So you will not be able to find the value of the function in the YZ plane. Same thing on the y, in the xz plane, y is 0. Therefore, our function will not be defined there. So if we want to graph it, basically, it will look a bit messy. So we'll just write the domain is the whole space R3 except the 2 planes, yeah, the plane YZ and the plane XZ, like this. Do you understand it? Yeah? Right, B, we can also have a look at this question B. Now, here we have a square root, huh? We have a square root. Now, so what does that mean? Yes, what you have under the square root must be greater than or equal to 0. So this function g will be defined only when y minus x squared minus y squared minus z squared is greater than or equal to 0. Now, let's see, what is this? let me take these three terms to the other side. It becomes 9 greater than or equal to x squared plus y squared plus, or let me write it in a slightly perhaps better way, x squared plus y squared plus z squared is less than or equal to 9. This is where the domain is. So the domain is all the points in the space where x squared plus y squared plus z squared is less than or equal to 9. Now, where are these points? Where are the points where x squared plus y squared plus z squared is less than or equal to 9? First, suppose I say, where are the points where x squared plus y squared plus z squared is exactly equal to 9? If it is equal to 9, what is this? Of course, you have 0, 0, 0, yeah, which is, but what is it if I put exactly equal to 9? What shape is x squared plus y squared plus z squared equal to 9? It's a sphere, yeah? It's a sphere of radius 3, yeah? So equal to 9 is a sphere of radius 3. Less than or equal to 9, where are the points which are less than or equal to 9? It's inside the sphere. Basically, equal to 9 is exactly the sphere. Less than or equal to 9 is inside the sphere. Every point inside the sphere will have -3 here, -3, 3 like this. So inside less than or equal to 9. Outside greater than or equal to. And exactly on the sphere, exactly 9, yes. If you take a point on the sphere, like this one, 0, 0, 3, then x squared plus y squared plus z squared is exactly equal to 9. Take a point outside the sphere, like this one, which is 0, 0, 4. What can you say about x squared plus y squared plus z squared? It's 16, yeah? It's going to be greater than that. Take a point inside the sphere. Can you give me a point inside the sphere? For example, on the z-axis. Let's stay on the z-axis. 0, 0, 2, yeah? Because the radius is 3. So we'll go 0, 0, 2. Find x squared plus y squared plus z squared. What is the value of that? 4. Is it less than 9 or greater than 9? Less than 9. So basically, when you have a sphere, you should remember this, that on the sphere, equal. Inside the sphere, less than or equal. Outside the sphere, greater than. That's it. So because our domain is less than or equal to 9, so this is inside the sphere. That is the domain of, yes? Sorry? Yes. Yeah, let me just explain this because it's really important. Let me re-explain this. Suppose you take this equation. Let me first work in 2 dimensions. If I have this, what shape is this? Circle of radius? 2, yes. Yeah. So that means every point you take on this circle, its x coordinate and y coordinate. When you square them, you get exactly 4. That's what it means. For example, let's take a simple example. This point will be the point 2, 0. What is x squared plus y squared? 4, yeah? 4. Yeah. This one also 0, 2. It's also 4. Any other point you take on the sphere, on this circle, will give you exactly 4. Now take a point inside, anywhere. For example, this one. 1, 0. If you take x squared plus y squared for that point, what will you get? 1, which is less than 4. So every point, so I can say this, on this circle, x squared plus y squared is always equal to 4. Inside, if you take any point inside, x squared plus y squared will always be less than 4. Now take any point outside, it will be greater than 4. Any point. This one maybe is about, what, 3, yeah, 3 perhaps. You will see that outside, x squared plus y squared always greater than 4. So basically, this circle, if you think about it, this circle divides this plane into how many regions? 3 regions. Inside the circle where x squared plus y squared will always be less than 4. On the circle itself, when it's exactly equal to 4, and points outside the circle will always satisfy the equation x squared plus y squared greater than 4. Do you understand it? That's exactly what this is telling us. By the way, this works with all the curves. For example, y equal x squared. Look at the curve y equal x squared. Here also we have 3 regions. We have the parabola. Every point on the parabola will be exactly, y will be exactly equal to x squared. Yeah? For example, the point 2, 4. Yeah, like this is on the parabola. Here, inside the parabola, we can check that if you take a point inside the parabola, y will always be greater than x squared. And outside the parabola, if you take any point outside this parabola, y will always be less than x squared. Like this. So any curve actually divides the plane into how many regions? 3 regions, yes. On the curve, it's equal, whatever the equation is. Then one region will be less and the other region will be more. Same thing with lines, etc. Okay. Now this is just the bracket we open regarding this. So let me go back a little bit to this idea of domain. Are we okay with this? Yeah. So the domain is inside the sphere for this particular function. Okay, this graphing, I don't think we have to be to worry about graphing. We will not be asked to graph. I just want to. Do you want to break, or shall we just continue? Do you want to break?
Yes.
All right, take a small break.